Yes, hello everyone. My name is Aidan Randtoul, and I'm going to talk to you about my paper, Reliability Benchmark for Actor-Based Server Languages. As you can see from my university and probably from my accent, I'm from Scotland, and I completed this work as part of my final year project alongside Professor Phil Trinder, who sadly is not here today, but as you see, he submits quite a lot of stuff. And so, just to go through a bit of background, with the size of the internet as large as it is and still growing, the importance and reliance on servers is massive. There's approximately over 4 billion users at the moment on the internet, and that's still rising, and there's still large parts of the world which are not fully connected. And with each of these users, they'll potentially access multiple services a day. So the number of requests that servers need to process every day is exponentially higher. An example of this, WhatsApp was mentioned earlier. 2014, WhatsApp reported that 64 billion messages were processed in one day, which is approximately 2.6 billion per hour. So that's just one service, and it's a massive amount. And so servers must support high levels of concurrent requests. And furthermore, with this high level of demand, the importance on reliability is even higher. If a server is to suffer an outage or have a disruption, then it can be extremely costly. It's estimated that the average cost of disruption at the moment is around $5,600 per minute. However, with larger companies, this scales up. And so last year in August, Amazon suffered a glitch that had meant that Amazon.com was down for around 13 minutes. And it's estimated that that cost the company $2.6 million, which is approximately $200,000 a minute. So it's very important. A key way that you can engineer servers that are highly concurrent and highly reliable is using actor languages and libraries. These are great as it allows you to scale up and scale down the service, but also they allow you to implement many different reliability mechanisms such as supervision and process isolation. And because of the popularity of them, there are now so many options for a language or technology to choose. And so the aim of the paper was to design a new benchmark that would focus on the reliability of these languages and technologies and allow someone to get a view over which one would be best suited to their needs. So back in 2018, Ivan Valkov completed a study into the scalability of server languages, comparing Erlang, Go, and Scala. And to do this, he created a benchmark called concurrent process throughput, which evaluated the scalability of the language and using a number of experiments. The benchmark works by spawning an array of process pairs which communicate with each other constantly. And then at the end of the benchmark, the amount of successful messages is tallied up and a throughput value is achieved. The results showed that each language has its own unique features, such as Go having the highest throughput, Erlang having the lowest spawn time, and Scala Akka could support the highest number of processes. And so this showed that each of these languages has their own unique strengths and weaknesses, and so we expect that this will be similarly replicated in our results. So now on to the benchmark that I created. We called it Supervised Communicating Processes, and it extends the SCPT benchmark in 2 key ways. The first is the addition of supervision to the system. Now, supervision is when another process is allocated to the task of monitoring a process and stepping in if a failure or a problem occurs. And so the way the benchmark works is first the head supervisor is spawned, which will spawn the aggregator for the system to tally up the messages, and then the head supervisor spawns an array of sub-supervisors, which they are a configurable amount. And then each sub-supervisor then spawns an array of process pairs, which again is configurable. The second key alteration is that communication is limited within the pairs to roughly 5 times per second. Now, this was done to avoid a potential scenario where the baseline throughput was affected by the kind of maximum amount of communication that could happen. And so one process pair experiencing a failure would actually allow other process pairs to reach a higher number of throughput, and so then the results would balance out and not make any difference from the failures. A second part of the experiment is the benchmark is the parametric fault injector, which is designed as an array of killer processes which send trigger failures in the main system, and they are able to be scaled up and scaled down depending on the requested failure load. It was designed to be run on a separate host/VM, and this is to avoid any resource competition with the main system, as I didn't want the amount of failures being induced to be affected by the other parts of the system. One key thing about the fault injector is it's designed to be deterministic, and so this sets it apart from the classic chaos monkey style that you'll have seen before, which are very undeterministic, non-deterministic, and we did this ideally so that we could reproduce the results and be able to kind of repeat the runs and be able to compare the results, whereas with something less deterministic, it would be hard to compare as the failure loads might be drastically different. The fault injector has 4 main modes, falling into 2 categories. And so the first is the progressive permanent category, which features failures where the process pairs are not restarted. And the mode in this category is progressive, and in this mode, a set number of processes are terminated at a set interval. And this was designed to reflect scenarios where a system is experiencing failures but continuing to run. Potentially, maybe you think of a scenario where a RAID array is being used and certain drives in the RAID array are failing, meaning that parts of the system are not operational if they're using those drives, but then other parts of the system might be able to continue. And so we wanted to have a look at the kind of process isolation implementation to see how these kind of failures would affect the other parts of the system. The second category is with recovery, and as the name suggests, this is when a process pair fails, it is allowed to be restarted by the supervisor. And the 3 main modes in this category are uniform, which is a single process pair is terminated on even intervals, and this is designed to reflect potentially a web server scenario where failures are more evenly spread, and it could be from users sending a request which is malformed or with incorrect information, which then fails when it is processed. The second mode is burst, and in this mode, a chunk of 25 active process pairs is terminated, and this is designed to reflect a scenario potentially like a network failure where a large amount of failures occur in a short space of time, followed by a period of potentially, if the network goes back up afterwards, a period of no failures. And then finally, we have the random failure mode, which was designed to be a more realistic scenario where a combination of different failure types can occur, such as potentially a network failure and then some more steady failures and then another burst of failures. And so it kind of combines the 2 above. So we designed the benchmark to be language neutral and allow implementations in many different languages. And for our experiments, we chose to look at Scala, Akka, and Erlang, which are both 2 very popular languages. Now, I'm not going to stand in here and explain what Erlang is to the Erlang workshop, but a little bit about what Scala and Akka is. Scala is a language that's built to run on the JVM. It's strong and statically typed, and it supports multiple paradigms such as object-oriented and functional. And Akka is a package which is very popular. It implements a series of concurrent models for implementing concurrency, and as well it implements distribution. So the reasons we chose these languages were 3 main reasons. The first being that they feature what is sometimes referred to as green threads, meaning that there's more fine control over the processes in the system. The second being they both support distribution, Erlang natively, and Akka Scala from the Akka package. And then they also support supervision. Again, Erlang supports this natively, and Akka brings that in for Scala. So just a little bit about the implementation. So in the Erlang system, the supervisors from OTP are used, and these are set up using the 2 variables, the subflag structure, which is a map. That's used to define the characteristics of the supervisors in the system. And so most of the values within subflags are set to default. However, the key ones that we have set are the restart strategy is set to 1-to-1, which means that for when a process pair fails, only that one is restarted. And also the restart intensity and restart interval are used to determine how many failures a supervisor can withstand before itself crashing. And so we didn't want to look at these variables, so we just set them to unreachable values for the system, just to remove that from any of the results. The child specs are used to define the children of the supervisor and the relationship between them, and so the only thing we decided to change in this was the type, which is either transient for the with recovery experiments, which means that they are restarted when a failure occurs, and then for the permanent failures it's set to permanent, meaning that when the process pair fails, it is not restarted. So a couple other things. The fault injector in the Erlang system utilizes the exit function to kill processes. This will trigger a failure in the process pair, allowing the supervisor to either step in or not. And then as well, to schedule the failures in the fault injector, we use the timer sleep function. This was very useful as it allowed us to schedule the failures as it's not thread blocking, and that means that it's not going to affect the rest of the system having the parts of the fault injector wait to run the failures. If you'd like to have a look at the code for the implementation, it's available at that GitHub link there. So I've designed it to try and be able for you guys to have a run of it yourself. This is how it works, and so I'd encourage you to do that. Just a little bit of code fragments. So just on the left here, we have the function to kill a process in the system. So just going through quickly the different things. The first thing it does is the function is given a supervisor, which is going to kill a process pair within. And the first thing it does is it gets a list of all the process pairs that sit under that supervisor. Then it will randomly choose a target within that list that is returned. And firstly as well, just one of the things we wanted to think about is whether if in systems especially where there's few supervisors, we didn't want the system to two killer processes to target the same pair and at the same time try and kill it. And so a small RPC call is used just to query the main system just to check it's still alive. And as long as it's still alive, it will go ahead and kill. On the right here as well, we can see just a little bit of the process within the process pairs. So they designated a client and server. This is purely just because one of them has a little bit more responsibility. The server is responsible for starting the system. Also, when a message is received from the other member of the pair, it handles that, and then at the end of the system, it will stop. Now on to a little bit about the Scala implementation. So for this, we use the object-oriented style of Scala, and from the Akka package, the supervisors used are designed to be Erlang style, and so that meant that all the variables mentioned before are set to exactly the same values, and this was quite good as it meant we could do a very equal comparison. Failures occur quite a little differently in the Scala system due to the absence of an equivalent exit function. I used arithmetic errors, which are induced, so essentially a message is sent to the pair, and when it reads the message, it crashes, allowing the supervisor to step in. And finally as well, there's also no equivalent of timer.sleep. There is a thread blocking sleep action, but that was not suitable for what we wanted to do, so we used the Akka scheduler. This worked very well, however it also has some drawbacks, being mainly that if a process schedules a message using the Akka scheduler, that process could then die and then the message still is sent. So in order to avoid this, we set up some fallbacks, which were a post-stop clause, which caught these messages trying to be sent by a process that's now died. And also we used a timestamp to make sure that the process pair wasn't trying to send a message to something which it knows is already dead. And again, the code is available at that GitHub link. And again, just the same two parts of the code, but in Scala. So the kill process function it works slightly differently. Due to Scala and Akka, you don't need to get a new copy of the processes because they have an ID which is fixed, and so when you restart a process, it just stays the same, so we didn't have to constantly be updating that. And so it just picks a target, same as before, randomly, and then sends a message to it to stop triggering the error, and then continues on. And just a little bit about this, the code line of code at the end. One thing we wanted to do is make sure that the kills were spread across the supervisors in the system. And so as a kill happens, it moves across the array of supervisors, meaning that it's spread out and all the failures aren't occurring on one supervisor and then all on another one. And then a little bit about the same snippet. I've removed some of the declarations at the top just because they're very long in Scala. But this goes through just the way that the server in Scala works. It's very similar. So at the top is the failure message. It's very simple. It just sends a 0 and then it tries to divide by 0, causing an error. The next is the starting command, then followed by a response from the other pair. And you can see here the time equals send time is one of the things we did to try and catch any incorrect messages that have been sent. And then as well, you can see it sends a message to the manager or aggregator, which will update the throughput. And so now on to the results. So we completed the two main categories experiments using the two categories of failure mode. So the first one we'll look at is the permanent mode. And so this experiment we called the progressive permanent failures. And in this, the key thing we were looking at was the implementations of process isolation. And so these process pairs are killed without recovery. And so just to explain a little bit about the graph you're seeing. So on the left, you've got throughput in messages per second. On the bottom, you've got time in seconds. And the blue line represents the Scala Akka results and the red line, the Erlang results. So in this, we are killing 5% of the process pairs in the system every 5 seconds. This, I appreciate, is very time condensed, but we did this to try and make the results more readable and understandable. And so what you can see from these results is that in both systems, the throughput is reducing in proportion to the number of processes killed. So therefore, in this experiment, for every 5% of the processes that are killed, the throughput is dropping by 5% of the original value. So this shows that there are very little effect on the rest of the system when you're killing a section of the system. And what we can see, there's a couple of interesting points though to note in terms of deviations from what we expected. The key ones are in the Erlang system, at around 40 seconds, you can probably see a kind of uneven drop. So we noticed this in all of our experiments, and we anticipate that this is some background memory management is taking place potentially due to an accumulation of processes that have been killed, and then something needs to go on in the background to clear the space that, or the memory that they were using. What you can also see is blue error bars, which are related to the Scala Akka results. And so one thing that we noticed was that deviations in the results were much higher in Scala Akka, especially at very high loads. I believe that's approximately every deviation above 5%. And so as you can see, the results in Erlang, apart from the drop at 40 seconds, didn't deviate very much at all. However, it was dominated at the top by the Scala results. And so we anticipate this is due to something that has been observed in the paper mentioned at the bottom there, which is that the message latency in Scala can be quite unstable, especially when the system is under higher loads. And you can see this as the graph goes down, these deviations reduce in size and therefore don't appear on the graph. So now to have a look at failures with recovery. And so as I said before, this is looking at the supervision implementations in both languages. And there's three main things that are varied by these results in this experiment. The first is the ratio between supervisors and supervisees. And this is varied between 1 to 124. We chose these values just to keep the scale linear. And this ratio bit essentially relates to one supervisor for every process pair, all the way up to one supervisor for the entire system. And also, as mentioned before, there's 3 failure patterns that are used. And then finally, failures are varied between 0 and 20%. We chose 20% as it was, well, it is an unrealistic value. It has been observed that failure rates that high can be experienced in short bursts. However, the kind of key area that you'd find and typical servers is kind of around the 0 to 10%. The first one we're going to look at is the ratio of supervisors to supervisees and burst failures. And so what you can see from these results is that it's critical to maintaining a high throughput that you have the right number of supervisors, especially in the Erlang system. As you can see on the left, well, actually I'll go through a little bit about what is on the graph. So on the left is throughput and messages once again. On the bottom is the number of process pairs per supervisor, so that's the ratio. And then each line represents a different failure load. And so on the left-hand side, you can see for the Erlang results that when you have very few supervisors in the system, throughput is affected quite significantly when you're experiencing failures. At 20%, you can see quite clearly how drastic a drop that is. And so we established from these results that essentially anything under 1 to 128 is ideal. And in the Scala system, you can see that having too few supervisors doesn't seem to have an effect. However, having lots of them, having a 1-to-1 or 1-to-2 ratio can increase throughput quite significantly. And so we established that these are the kind of ideal ranges, and you can see as well in the Erlang results for burst failures that more supervisors is also beneficial to throughput. This potentially suggests that having more supervisors means that a burst of failures can be processed much more quickly. But however, having too few in Erlang means that there's not enough supervisors to process all the failures. So having a look at random failures, you can see a slightly different story for the Erlang system. There is no benefit to having more supervisors. However, there's still that same drop in throughput having too few. However, across the board, you can see that throughput reductions are quite small, even at higher failure rates, as long as you select a suitable value for the ratio. And interestingly, in the Akka results we found, the Scala Akka results, we found that there was no effect whatsoever of the number of supervisors. The fluctuations you can see are very much due to the message latency, as mentioned before. And so in this, it's just a more general picture, and you can see as well, even in these results, when you've got a suitable ratio, the drop in throughput is less than 12%, even when experiencing failure rates of 20%. Now, just to mention, I didn't want to fill the presentation all with graphs. So the uniform failures show similar stories in different ways. So for Erlang, the uniform failures is basically the same graph as the one on the left just there. However, for uniform failures in Scala, it shows a very similar story to burst failures, which is an interesting difference between the two languages. And now just to have a little look at comparing the patterns. So first I'll have a look at Erlang. And so you can see that in both graphs that the systems are able to withstand the failure rates in all modes. However, there are strengths for the system. For example, if you can see when you've got the 1-to-1 ratio, the system on the right, the Erlang system on the right, has a much higher throughput for burst failures. And you can see also that for the random failures, it's slightly higher than uniform, so with the random failures, the bursts are up to 10 in size. And so this indicates potentially as the bursts get bigger, then the number of having extra supervisors makes the throughput be maintained more. And so potentially if you increase that value, it could rise closer up to the burst failure. And then on the left at 64 process pairs per supervisor, you can see the results track each other very closely. And yeah. And so looking at Scala, it's quite a similar story. So at 64 process pairs per supervisor, you can see that the results are track each other very closely. However, it's noted that the uniform failures is slightly higher, which is something that we kind of observed across the different experiments. And you can see on the right even further, when you have a ratio of 1-to-1, the Scala system much prefers that. And potentially, we think this could be due to the supervisors in Scala Akka having less overhead, especially due to in Erlang, the supervisors are another process in the system. So potentially in Scala Akka, relationship is a little bit less resource intensive, meaning that where in the Erlang system you'd have a drop in throughput for having too many you didn't get an increase in throughput for having lots of supervisors. In Scala, you do, and so this was something very interesting we spotted. And so finally, to move on to the final set of experiments. So one thing we just need to mention was, as you might have noticed, when you're looking at the two graphs, the baseline throughput of the two systems was different. There was approximately a difference of about 10%. And so in order to directly compare the two sets of results, we had to normalize them. And we did this by taking the results as a proportion of the baseline rather than just the actual throughput value. And so when we do this, we can see a direct comparison between the two. And so the first graph we'll look here is when you're experiencing burst failures. And so what you can see here is that the results are very similar at the two different ratios. I should mention on the left here, you have the proportion of throughput retained. So if it starts at 1, and then as you go down, you can take that as the percentage drop in throughput. And then you've got the failure frequency on the bottom, and the dotted lines are the 1-to-1 and the solid lines, the 1-to-64. And so you can see that in Erlang and Scala, the results at 1-to-1 are very similar, both experiencing an increase in throughput when you have more supervisors. However, when you've got the 1-to-64, the throughput is lower, but it still only drops to around 10% less. When you think you're experiencing twice that many in failures, it shows that both systems are able to maintain throughput well. And especially in the burst failures, in the 1-to-1 ratio, that throughput is dropping only 4% when experiencing 20% failures. So it shows that if you're anticipating your system might be experiencing this type of failure commonly, then it's a real benefit to have more supervisors in the system. So moving on to uniform, this was definitely the most interesting set of results. As you can see, as a whole, the Scala Akka system performs much better, especially at a 1-to-1 ratio. As you can see, the dotted line in blue, it's only just over 3% reduction for 20% failures. And so this was really quite quite a lot of throughput was maintained for that experiment run. Again, you can see the next one down at 20% failures is 1-to-64. However, the one thing to notice is that for the Erlang system, at lower failure rates under 10%, you can see that the 1-to-64 performs better. And so we anticipate that as the failure rates would increase, this would continue and they would kind of diverge. However, maybe at the lower end, there's a benefit to picking Erlang over Scala in this case. And then, as mentioned earlier, thinking that there's more overhead from the Erlang supervisors. This is demonstrated here as the 1-to-1 results for Erlang were much lower, very quickly dropping below all the other results and continuing to stay below. And so, yeah, looking at that, it's uniform failures is the key area where the results diverge, with Scala clearly having a benefit, especially if you pick the best ratio for it. And then finally, just have a look at random failures. The throughput, again, is very similar. However, there is one key key results, which are the Erlang system at 1-to-1. Again, as I've mentioned, I think the general theme we saw was that having more supervisors can have a detriment to the Erlang system, whereas in Scala, it's only really positives. And so as you can see, the results are slightly lower, any failure rate above 2.5%. And then for all three other sets of results, they've maintained the same course. So to summarize, the first thing we looked at was defining a new benchmark for actor-based server languages. We believe that this is the first benchmark of its kind. And so, after that, we implemented two implementations of the language in Erlang and Scala. Then completed a series of experiments, the first one being progressive permanent failures, which showed that both systems implement process isolation very effectively. Then we looked at the recovery from different percentage failures, and this showed that when you've got the ratio, the different ratios have strong points. So 1-to-1 in both Erlang and Scala prefers burst failures and has a higher throughput. But then when you look at uniform failures, the Scala Akka system as a whole performs higher. And for random failures, it's a combination of different results, with the Akka system not having much difference to having more supervisors. However, the Erlang system having more supervisors does give it a slight performance increase. And then finally, we had a look at the normalized comparison between the two. And so overall, those results showed that there was an increased overhead from the Erlang supervisors, but also based potentially on some of the results, it looks like there may be a slight increase in the effectiveness of the supervisors in Scala Akka, meaning they are able to process them quicker. That could also be due to could be the reason for the uniform failure results. And so there's quite a lot of factors, but it showed that definitely the languages have their strong areas, their strengths and their weaknesses. And just to go over a little bit of stuff that we have kind of penned in for future work. So the first is we wanted to have a look at some other languages. So the key ones we thought about looking at next would be Java with the Akka binding, and also Elixir. And then doing this for doing the experiment for those two languages would allow us to get a 4-way comparison. And then next we would have a look at some of the variables that we kept the same for the whole experiment. So in terms of recovery strategies, we could have a look at the one for all and rest for one strategies, which rest for one will restart all dependent processes when one fails, and then all for one will restart all processes underneath a supervisor when one fails. And so we expect this could have a significant effect, because not in our system we've assumed all the process pairs are stateless, and having one of them crash doesn't affect all the others. And so it's very likely that a more realistic system will have dependencies that could be affected. And then we had also thought about having a look at the type of failure. So within the Akka system, as mentioned, we used the arithmetic error. Potentially other types of errors may be more catastrophic and affect results if the supervisors need to do more work to restart them. So that would be something to look at. And then finally, the biggest one probably would be to look at recovery of entire VM failures. We just looked at processes within one VM, but thinking about how long it would take to restart an entire VM, that can be something that would be very interesting to look at, and an extension to the benchmark could allow this. And so that's everything I've got to say. So thank you very much for listening, and welcome any questions.
Thank you very much, Aidan. Are there any questions?